All right, so our next right-hand rule problem is very similar to the previous ones, but a slight twist. So now we have a moving charge, and it's negative charge, so we'll have to make sure that we remember to flip the sign. But we haven't been told the direction of the magnetic field. Instead, we've been told that this negative charge is suspended between two magnets. So we know that magnetic fields point from north to south poles, so that means that everywhere between the magnets, there's a magnetic field that points to the right. So we have B and V, and we're trying to figure out F. So we'll use our right-hand rule again. So I'll do my palm for V, twist my hand so that I can get V to, I can do this, get V points down, B points to the right, and my thumb is pointing out of the page. So we'd expect a positive charge to feel the force pointing out of the page. So this is a negative charge, so it should feel a force pointing into the page. Next is a kind of primer to a Lenz's law type question. So magnetic flux. This is, if you want to think about the analogy in class, with a fan and a loop, the magnetic flux would be how much wind goes through the loop. So magnetic flux is this guy, and it depends on the strength of the magnetic field and also the effective area, so sort of the area of the loop that's actually perpendicular to the magnetic field. So for this, is the magnetic flux changing? For this one, I'd say no is probably the answer. As we move this through here, as long as we can assume that this magnetic field sort of continues on into this space, as we move it, it's just going to be kind of, it's still going to have the same amount of area exposed to the same uniform magnetic field. If this was a question on the test, I would hope that it would be much clearer than it is right now, because it's not obvious to me that this magnetic field doesn't just stop here. So if this magnetic field did just stop here, then the magnetic flux would change as it moved from in the magnetic field to out of the magnetic field. So I think the answer that was expected there was no, but if you had answered yes because you thought that it was actually exiting a magnetic field, then I can understand why you did that. This one here is definitely a yes. So as this loop rotates in the magnetic field, the amount of area that is sort of as this thing rotates, there's eventually going to be a spot where the loop has rotated to where it's completely perpendicular to the magnetic field, and there's no magnetic flux through that loop. Next one is a full Lenz's law question. This was a question that we did in class where we had to figure out the magnitude. I crossed off the magnitude here because that won't be on your test. All that would be on the test is using Lenz's law to figure out the direction of induced currents. So I have a loop, and we want to determine the direction of the induced current. So let's do this one first. And this is a loop that is in the magnetic in a magnetic field, but it actually has no magnetic flux through it. So there's no magnetic flux here, so there can be no induction. So here there is no induced current. Here there will be an induced current. So we have a loop that is got a lot of area exposed to the magnetic field, so there is a magnetic flux to this loop, and the strength of the field is changing. So because the strength of the field is changing, we will induce some current in that loop. So when we did these in class, we did them step by step. So I said that the magnetic flux is out of the page and increasing. So because, and we call this the external. So the external field is out of the page, therefore the magnetic flux, the external flux is out of the page. And because it is getting stronger, Lenz's law says that the induced field will oppose the change. So the flux is, the field is getting stronger, so the induced field will be the opposite of that. So in the interior of this loop, I expect to have some induced field that points in that direction. And now this becomes a right-hand rule question. So I'm going to put my thumb, imagine putting my thumb right here on the bottom, pointing so that my fingers are into the page in the middle of the loop, and I can see that my thumb is pointing in that sort of a direction. So the induced current is clockwise. And we have one more review question before we get to sound, so I may as well throw that onto this video as well. So this is, I have a transformer. It has 360 turns in the primary and 100 in the secondary. The primary coil is connected to 120 volts and draws 2 amps of current. What kind of transformer is this? So I have that the primary coil has 360 turns and the secondary has 120 turns. More turns in the primary means that this is going to be a step-down transformer. Okay, so for what voltage is in the secondary, there's a few equations in your equation sheet that would figure this out. So the secondary is going to be the voltage of the primary times number of coils in the secondary over number in the primary. So that's 120 over 120 volts over 360 volts. And that is 40 volts. So don't let the AC here mess you up. Transformers only operate on AC current, so it's necessary that it says AC here. If this was a DC current, then there would be no current or voltage in the secondary coil. So transformers operate based on the principle of induction. So if the flux isn't changing in the way that we get a changing flux with the transformer is by having the current and therefore the fields and everything be constantly oscillating. So without AC, this doesn't work. All of these things assume that you're working with AC current. And so what current is present in the secondary? That's a different equation also on the equation sheet. So I'll look at the current in the secondary and that is going to be 2 amps times 360 volts over 120 volts, and that's about 6 amps. So just to reiterate, the step down, it steps down both the number of the turns, so fewer turns is a step down transformer, also a smaller voltage is a step down transformer. So we started off with 120 volts in the primary, and we ended up with 40 in the primary. Step down transformers step down the voltage. They actually do the opposite. They step up the current. So you're always kind of doing the opposite to the current to what you're doing to the voltage.